21 today. So we learned last time about the simple regression model, or SRM. And we also learned that we're looking for a linear shape, just like that, of the scatter plot. We want less variation. You can see that the variation is pretty much good. We don't have too much variation here. And actually, that's a good thing. The goal is to come up with the estimation of your response variable given for a value of your independent variable or explanatory variable. So to create that model, or SRM, or simple regression model, for the association in the population between an explanatory variable and response variable, we're creating that regression model. So we learned that this is a linear relation in average. And what that means is that the relation may not appear to be perfectly linear, but in average, it is a linear relationship. And then you remember we did talk about the formulas. So you need to be good at these because there will be questions on homeworks and your exams on those notations. So, and you learn that anytime you are doing estimation of your response variable, that estimation is not exact. There is error involved. So that error we show it with epsilon. And we want to make sure the expected value or average of epsilons is 0. And how that happens? That happens when you have approximately same amount of points below the line, same amount of points on top of the line, pretty much symmetrical, same variation on both sides. The line goes through the data, and those points below the line, they are negative epsilons, negative errors. Those on top of the line, they're positive errors. Positives and negatives, they cancel each other, and that approaches your expected value of your epsilon values to 0. Another name we had for epsilons was residuals. So residuals are the errors of our estimation of the regression line. So there are three important assumptions. There are three important assumptions for the simple regression model, or SRM, to be reliable. And what do we mean by reliable? We mean if you make a decision based on this regression model, based on this equation, you want to make sure that this decision is accurate. It should be working at least for 95% of your population. So if you want to let that happen, you need to make sure your SRM follows these three assumptions. And these three assumptions has to be true for your model. So first of all, these three assumptions are about the residuals. And why are they about residuals? That actually shows how the line goes through the data and how the variation of your residuals, how far these residuals are distributed around the line. Are they very far from the line? That reduces the accuracy of your model. Are they close to the line and spread around the line? That increases the accuracy of your model. So these residuals are supposed to be independent. Or in other words, we don't want them to have a pattern, right? Pattern means from left to right, by changing your X value, by changing your explanatory variable, you don't want these errors, these residuals, keep changing in a certain way. They have to have same amount of changes. There has to be no pattern when you change the value of X. You need to have equal variances, meaning that the range and the variance and standard deviation of values when you change the explanatory variable should not change a lot. It has to be pretty much controlled in a certain range. All errors have the same variance. And you remember variance is square of standard deviation. The other one was you want to make sure that these residuals follow the normal probability distribution, and they will follow normal probability distribution if most of these residuals are around the line. They're close to the line. The line is considered the center of your normal distribution. So if this curve is the normal distribution, the center is the line, and you want majority of data around it, right? 68%, one standard deviation of residuals far from the line. 95% of them, 2 times of a standard deviation of residuals around the line. So that's what we expect to see. If that happens, that means majority of your residuals are actually very close to the line, and they're in a controlled shape. So one more time, remember, these 3 are very important because basically any other regression model we explore together for the rest of the semester, at least you need to check these 3, at least. So are there any other assumptions to check? Yes, there are other assumptions to check, but these 3 are, every time you want to do any regression analysis, even ANOVA and COVA, you still need to check these assumptions, because basically all of these analyses are somehow dependent on regression model. So make sure you know how to, and I'm going to show you how to do these checks on job. So let's move on to here. So this is the notation for a regression model, including the errors. So remember in the previous slides, we had estimation of y, right? Because the epsilon wasn't here, because we had an error. Let's assume that now we know that amount of error. If you know that amount of error, add it to the right-hand side of the intercept plus slope times explanatory variable, plus the epsilon, plus the error. That will be the accurate value for y, okay? So, and what does this notation mean? This means epsilon follows normal probability, n stands for normal probability distribution. Epsilon follows normal probability distribution with a center of 0 or average of 0, and standard and variance of sigma square, variance of sigma square. And this is actually representing our assumptions, right? Being normal, independent, and having similar variances. So the observations are independent, have equal variance around regression line, are normally distributed. That's what this means, okay? Once again, we will repeat this many times, including this one. We always check, this is our checklist for regression model to make sure it's reliable. And reliable means when you make a decision, it has to work for at least 95% of your population. So is the association between y and x linear? So we want to make sure the scatter plot looks a linear relation. Have we ruled out lurking variable? Is there any lurking variable? Is there another variable that has a strong association to both IV and DV, or explanatory and response variable, that is actually affecting negatively on accuracy of a model? So we don't want lurking variables, right? Are there errors? Evidently independent. Are the variance of residuals similar? Are residuals nearly normal? So checking these conditions using technology, the first thing we see here is that's your, on the x-axis is your explanatory variable, is your IV. On the y-axis, instead of having response variable, you're going to use residuals of the response, right? So you're graphing residuals to explanatory variable or IV. And what you want to see here, this horizontal line going through your residuals. So these are showing your residuals and how far these residuals are from the line. Are they spreading around somehow with the similar variances? Is the variation from left to right the same? It's approximately the same. The range, see, it doesn't change that much. When do we say it's too much variation? Normally, when there is high variation, you will see a triangle. Triangle means on one side you have a very close values to the line. On the other side, you have very wide range of numbers around the line. So in this case, we can say we have linearity satisfied. We don't see a pattern. How would it look like if it was a pattern? Pattern would look like maybe residuals start from below the line, and the more we move to the right-hand side, they move up. So that would be like a pattern. Left to right, it goes up. Or left to right, it goes down. These are pattern. Or they go down and then they go up. These are patterns. But here, they're spread around almost everywhere, right? So what shape do we look for to say that these residuals are spread almost everywhere the same? We can say these are actually look like a rectangle. This is approximately like a rectangle or like a circle, and has to be symmetrical on both sides, which this case it is. So we have the similarity of variances as well. So from left to right, there's not much change. You can put a line here on top and bottom, and they all fall in between. Spread of residuals constant around horizontal line, and that's what we adjust. So these are just being repeated because of their importance, okay? So we don't want lurking variables, especially obvious lurking variables, without knowing more about the context. We can only guess at lurking variable. What that means is there are topics that if you're not expert in that topic, maybe medical sciences, and if you're given some data about medical science, something that you're not aware of, what other variables actually can be involved there, right? In that case, what happens is because of lack of knowledge about other factors involved in your relationship, you might not be able to guess what other variables could be having some kind of a strong relation to your IV or DV. So as a result, it's very important to recognize a lurking variable. You have to have a good understanding of factors affecting your relations in that topic and about your data. Evidently independent. So is there any reason to believe that the time needed for one run influences those of others? If data are time series, plot residuals over time, and time, you can use a standard time like just 1, 2, 3, 4, and each value can be considered as a day or as an hour or as a week. Another condition that we check from SRM is normality of residuals. So one of the methods that you can use to find out if your residuals follow normal distribution or not is normal quantile plot. Some softwares like SPSS, they call this QQ plot. So if you heard QQ plot or normal quantile plot, they're the same thing. They help you to understand if your residuals are normally distributed or not. So that curve on the top and bottom, these are your upper and lower bound of normality. So are all these points in between the two upper and lower bound? If the answer is yes, they're all in between, the system is in control. So it's normal, right? This is normally distributed data. So here it says that nearly normal conditions satisfied. Why it says nearly? What is the perfect normality? It's perfectly normal if all of these points are exactly on the line. If all of these points are exactly on the line, that's a perfect normality. However, even if they are outside that line, they're not on the line, but they are between the upper and lower bound, that's still considered normal. Are there other ways to Check normality of residuals. Yes, histogram is one way. Checking skewness and kurtosis of your data. You can get them from descriptive statistics. If those values are exactly between -1 and 1, that shows that you have somehow normality of residual, especially skewness. If it's between -1 and 1, based on many references, we can consider them normal. There's another method that I'll teach you next time, that's Shapiro-Wilk test. And Shapiro-Wilk test for normality gives you a p-value. So you can actually pretty much with a borderline of p-value say that these residuals are normal or not. Of course, for homeworks and exams, you're expected to use this figure, this graph. But if you don't have the plot, are there other more accurate ways? Or if the plot doesn't perfectly show normality and you're not sure, is there a way to perfectly understand if the data is normal or not? The answer is yes. And the test is called Shapiro-Wilk. I type it in the chat. Shapiro-Wilk test for normality. So this test I will teach you next time. This is actually Shapiro. Okay, I will teach you that next time we meet for chapter 22. So modeling process. So what are the steps to create our regression model? First, plot y versus x. So y for response, x for explanatory variable, and make sure that you have a linear association. And how do we check that? We want to make sure we see a line. We don't want a curved relation, right? We don't want a relation that is like a rectangle or a circle, which they're not representing in linear association. Fit the least squares line and obtain, so that's your fit line, right? Obtain the residuals. And plot the residual versus x, and x is explanatory variable IV. So on x-axis you have IV, on y-axis you have residuals. You're going to look for similarity of variances. You're going to look for no patterns in residuals and majority of data to be around the line, symmetrically on top and bottom of the line. If time series data, construct a time plot. So we will talk about time series data in chapter 27, hopefully by the end of the semester. Inspect histogram and quantile plot of residuals to check the normality of your residuals. And inference. What do we mean by inference? So we did talk about hypothesis testing last time. If we are talking about association or relationship, there's a certain way of explaining the inference. And inference is what do we in general conclude from our data, from these relations or scatter plot or results of the regression line, right? So at the end of the day, we want to see if there is a significant relation between explanatory variable and the dependent variable, right? So I type in the chat. The question is, so that's your hypothesis. So hypothesis alternative will be, there is a significant relation or association between x as your explanatory variable and y your dependent or response variable. So I put IV and DV here to write in a short form. So since in this hypothesis alternative for relationship between two variables, I did not say which one is this relation positive or negative, right? In this, and let me type the HO as well. HO is exactly the same. You just make it in a negative form. So there is no significant relation between X, IV, and Y, D. Right? So we hope that we can reject HO, and that means there is a significant relation. Now, there is no pattern, or there is no explanation of if this relation is positive or negative. This is what we call it a two-tailed hypothesis. Since we don't have any explanation of this relation is positive or negative, as a result, there are two possibilities. This relation could be positive, could be negative. How do we know it's positive or negative? We look at Pearson correlation R. If R is positive, that's a positive relation. If R is negative, that's a negative relation. So since we did not mention anything and there are two possibilities, that creates a two-tailed hypothesis test. How would a one-tailed hypothesis look like? It would be like there is a positive relationship between these two variables, or there's no positive relationship between these two variables. So for this course, I can say 99% of cases that you will see, they are going to be two-tailed. We just look at there is a relation or there's no relation. If there is any question about positivity or negativity of the relation, that will be asked separately on a separate problem. So looking at the notations for SRM, I told you intercept is represented by beta 0, beta 1 is for a slope. The regression line, estimation of the line is mu of y given for a specific value of x. Deviation or residuals are represented by epsilon. Standard error or standard deviation of epsilons. Standard deviation of epsilons is called standard error. So standard error is represented by SE or sigma of epsilon. This on the data side is also the same. Beta 0 is the same as B0. Beta 1, B1. They're both slope. Y hat represents the line itself, the estimation of your response variable. Deviation or errors are represented by E. SE is standard deviation of the errors or residuals. Okay, so this part is pretty much important to understand. So you don't need to memorize this formula. You can always check back from the book, or you can check back from, in fact, the slides. But understanding this formula is important. What is SE? SE, we just talked about it, right? SE is standard error of slope. So that means what's the variation of errors or these points away from the slope? How far they are from this slope? Of course, we expect to have a less variation, right? So looking at this formula on the right-hand side, which is if you have a large sample, n-1 and n, they don't have much difference. So this is telling me if a value in the denominator like n, sample size is a big number. If denominator is a big number, the standard error is going to reduce. That means less variation. Higher sample size, higher n, lower standard error. Another thing, what is SX? SX is the standard deviation of, SX is standard deviation of X values, explanatory variable, right? It's in the denominator. So higher variation on X values, the more variation in your independent variable, in your explanatory variable, the lower the standard error, the lower the variation of B1, right? And lastly, standard error of the whole equation of a regression model, all your residuals together. If you get their standard error, the higher it is, that means higher variation of data. Higher variation of data that actually creates a higher variation of estimation of B1, which is not good. So the ones on top are supposed to be smaller to have a better model. The ones in the bottom of the equation or in the denominator, they're supposed to be larger to have a better model. So this standard error of B1 is actually influenced by standard deviation of residuals. As it increases, the standard error increases. Sample size, larger sample size, that means lower standard error or less variation. Standard deviation of x or explanatory variable, as it increases, the standard error increases. So you can see here, this two show variation of x, or variation of IV, variation of explanatory variable. When you have less variation in explanatory variable, you can see that you can create more lines that represent the same data. And they all can be very close and be correct, but when you have wide range of x values, you can see that all these lines, they pretty much are close and represent the same thing. And here we are with inference and regression. So when it comes to inference and regression, again, inference means the hypothesis testing, generalizing. Inference means generalizing. So in general, is there a significant relation between these variables? Or there is no significant relation between these variables, right? That's the question. How do we know? The first thing you look at is the p-value. If the question gives you a 95% confidence level, for a 95% confidence level, we look at the p-value. Are they below 0.05? If yes, you reject HO. So as a result, I type it in the chat. If the p-value is less than p-value less than 0.05 for a 95% confidence level, then reject HO. What was HO? HO was there is no relation, right? We are rejecting it. That means there is a significant relation. So if these two are below 0.05, both of them, intercept and the slope, intercept and slope, if they're both below 0.05 on p-value, that means this relation is significant. There is a significant relation. And that's actually showing that this model is reliable, okay? But we also have to check all those assumptions as well. What else can we check here? R squared, 85%, 85.6% of variation in your DV, in your response variable, is explained by the IV, and that's a good value. That's a good amount. More than 50% is good. That shows that majority of your variation changes in your response is actually coming from your independent variable. That shows your independent variable has a significant influence here. The standard error should be a small value, especially compared to B0 and B1. In this case, is not that much low, but still it's much lower than 171. So, and the main reason could be we have a small sample. We have 47 samples only here. And of course, if you increase your sample size, you will have a better standard error, okay? So let's move on and look at the confidence intervals. So confidence intervals is actually kind of a margin of error on any value that you calculate. If you calculate an average, there is an upper bound, lower bound around it that tells us what portion of other samples we select, they fall into this range. So we are actually creating a range, calculating a range, an upper bound and lower bound around the number that we estimate to make sure if we select a different sample with the same size of sample, that average, that number for that other sample is also in the same range. So when we say 95% confidence level, what we mean is if we select any other sample from this population, they're going to have slope and intercept also in this range that we're calculating. So as a result, we calculate the confidence interval for intercept and add it here. Of course, that confidence interval has to be around 171 plus minus 2 times standard error, right? So where's the standard error of intercept? Is right there, 40.8. Where's the standard error for slope? It's right there. Again, I hope you remember the standard deviation topic. Approximately 95% of your observations, and in this case, your errors, they fall between 2 times of a standard error plus and minus 2 average, which is intercept or slope, right? Approximately 2 times. And I say approximately 2 times because depend on sample size, this 2 can be like 1.96, 1.962, it can be 2.04 and so on. But it's going to be somewhere around 2. And for calculations, we normally get a number for t, we get a number around 2 times standard deviation around average. So this is the same what you learned at the beginning about standard deviation. That's your estimated value, B1 or B0, plus minus approximately 2 times of standard deviation. That includes 95% of your data, okay? And in this case, you see that we said approximately 2. In this case, is 2.014. And let me really quick show you how to get that number from Microsoft Excel. So this is 2.014, and let's see what's the sample size. Sample size is 47. Okay, 47 is n. And we have, so we're going to calculate the t stat. And the t stat equals to, so all you have to do here is, let me just zoom in a little bit. Type in t and t dot inverse. So t dot inverse will give you the t value for a specific probability or confidence level. So in this case, confidence level is 0.95, but Excel gives you one tail. So to calculate for a 2 tail, you have to add half of the significant level alpha. What's the significant level here? Significant level or alpha is equal to, perfect, 0.05. So you calculate half of it, right? So half of significant level is going to be 0.025. You have to add this to your confidence level, right? So add it to confidence. What is the confidence? 95% or 0. Oops. Here, add it to 0.95 or 95%. Okay, so that would be so for 2 tail use 0.975 instead. Perfect. Okay, so t stat is going to be equal to and type t dot inverse. Probability is 0.975 and degree of freedom. So degree of freedom for regression is n minus 2. We have 47, right? 47 minus 2, 47 minus 2, 45. 2.0141. Let's look back here in the slides. .014. It rounded the other decimal, right? So where did that number come from? It's a t stat. You take it from t-table. T-table, I hope you remember t-table from basic statistics, or use Microsoft Excel, or some of your calculators actually has this value. At the end of your book also has a t-table, so you can check it out. But I think the easiest one is using Microsoft Excel. Really quick, you can calculate the t-value. If you were really didn't remember, there are websites that you just plug in the confidence level and sample size. It immediately gives you the t-value. So that's not a problem. And then where did the 0.149, what's that number? That's standard error, right? That's your standard error, SE. So SE of B1, slope, SE of B0, intercept. Each one has its own standard error. Look, intercept, standard error, STD error is a 40, right? 0.86. Standard error of your slope is 0.149. 0.149 and 40.8 is coming from there. And the jump results also have this number for you. All you have to do is to find the t-value, multiply it, and add it to intercept or add it to your slope. And you can calculate the confidence interval. So this confidence interval actually jump calculated for you automatically. You just click and add it. I will show you very soon. Another way to calculate the t is B1 itself divided by a standard error of B1, or B0 divided by a standard error of B0. For beta 1, 0, for beta 0, 0.
Yes, sir.
Give me 1 sec. Let me just. All right, so let's move on to. So that's the p-value I told you. If it's less than 0.05 for 95% confidence level, you will reject HO, and that means there is a significant relationship. P-value is not the only method you can use to find out the relation is significant or not. I will show you when I'm explaining in JMP that what are other ways to do that. And actually the book explained it too, so I expect you to read the book and take note of those topics. And checking assumptions again and again and again. We always check assumptions, normality of residuals, checking similar variations, independence of residuals as well. So the confidence interval that we just talked about, it was for the confidence interval that we just talked about, it was just for slope and intercept. So we have other confidence intervals. So when you see the questions that they ask you to calculate confidence intervals, it's very important that you remember which one we're talking about. So right now we just did confidence, CI means confidence interval. CI, we just did the CI we have for intercept. So you have to see which one the question is asking. We also have a CI for slope. And we have CI for the prediction formula, or we call it, we call it prediction intervals. Prediction intervals. Okay, so prediction intervals are actually vertical confidence level on top and bottom of the line around the y-axis. What you just learned about the slope is not around the y-axis, right? So prediction interval is you're creating a confidence interval around y-axis. So what is a prediction interval? An interval designed to hold a fraction, 95% of the values of the response. So this is 95% of the response. Okay, this is very important to remember because there will be questions on homework and exams. that if you don't understand this well, you will keep calculating confidence intervals and you will get it wrong. So it's very important to understand this prediction interval is the confidence interval, normally 95%, around the response, around your dependent variable. And what is it for? For a specific value of x. So x is not in general. For a specific value of x, or a specific value of independent variable, or explanatory, the value will be given, and we will ask you to calculate confidence interval for the response. And some questions will say confidence interval for response. Some will tell you to calculate the prediction interval. Okay. How do we do the calculations? That's the formula. I know it looks a little scary, but it's nothing. X new is the X value that the question will always give you. It will tell you for this specific value of X, find the prediction interval. And to find the prediction interval, you first need to find the new value for Y. So new value for X is given, substitute in the regression model, it will give you the new Y. You have the new Y, you can actually calculate the standard error of Y. The standard error of Y is the standard error of the whole model, 1 plus 1 over n is sample size, plus the new x minus the average of x values, a square, divided by sample size minus 1, multiplied by variance of your x values under a square root. So you calculate a standard error of a new y value, that's here, approximately 2 times of it, plus minus the y new that you just calculated there, that will give you the confidence interval. Does JMP calculate that? Yes, JMP calculate that for you. So show you where to get that number. That's why I want you to pay attention today, because there are lots of these formulas that are quite tough. With just 1 or 2 clicks, you can get the answer. You don't need to do the actual calculation. So one of the students is asking, is this prediction interval based on the prediction from the regression line equation? Exactly, yes. That's actually based on the equation. That's what I showed you here. Told you that you substitute the new value of x into the model. So B0 and B1 are the slope and intercept that you got it from the results, multiplied by your new value, add it to intercept, that's your new y value. Now you want to create a confidence interval around it. That's how the calculation is, but actually JMP calculates it for you. And this 2 is approximate, right? Approximately 2 times standard error around the y values. So prediction intervals are reliable within the range of observed data. They are also sensitive to the assumptions of constant variance and normality. So if for any reason you forgot what confidence interval is, confidence level is, what p-value are, I did discuss these topics earlier in the past weeks, and the records are available. Please watch those videos before you jump into here, because understanding what this confidence interval represents is actually important to answer questions. Okay, so I think we can jump to our JMP and start working. So look, this is the prediction intervals is actually vertical around a specific point of x. So a specific point of x is given, an individual value of x is given, you calculate an interval for it, a confidence interval for it. And that confidence interval just works for that individual value. So how reliable your model is, this is a good example here. So this is a case with that follows, the linear regression here follows those 3 SRM assumptions that we said: normality of residuals, similar variances, and no pattern in residuals, right? Or random residuals. So if these 3 have met, you will have this. That means your regression line, including the upper bound and lower bound of your confidence level, covers majority, at least 95% of your data. But in this case, you can see, seems to be a curve relation because of lots of outliers, and that you don't have similar variances here. You can see the triangle here. I told you, whenever we don't have similar variances, we will normally see a triangle here. So that triangle is telling us this, we don't have similar variances and as a result, this line is not really representing this relation for us. You have this data in your data set, data folder. So weight of diamonds versus the price of it. Is there a relationship here? So really quick, let's look at fit y by x. Most of the things that I'm showing right now, these are just repeat from the past. So I do it really quick. Your weight goes to X factor or exploitative variable, price. You want to see if it's influenced by weight. That's it. You just plug them in and click OK. Well, you can see that that association, that problem that we just talked about exists here, right? But let's just practice and see how we can get those numbers. The first thing we look at, so linearity, well, approximately linear, but we don't have similar variances. Summary statistics on the red triangle will give you the correlation value of 84%, or 0.84. It is a significant association and it's strong and positive. Moving to the right, it's increasing. We also see the average and standard deviation of price and weight. So you can see that the price has a very high variation, 1,079. That's a lot. So that's actually showing this variation in here. So we need to also add the fit line. So that's our fit line. That's the regression model. That's your y hat, which is estimated price. That's your B0 or beta 0. That's your slope. And that's your independent variable or x. What's the R square? R square is 72% of variation in response variable price is explained by variation in weight. Okay, so where's the model? Let's just quickly get this. Make this smaller so it fits here. Okay, so move down. Move down here. We have intercept and the slope. These are the estimation. This is your B0. This is your B1. These are the p-values. Is there a significant relation here? The answer is yes. There is a significant relation. Reject HO, and the association is significant between weight and price. So weight has a significant association to price according to this model. So the model is reliable at this point. Let's check some assumptions. So before checking assumptions, really quick, we had a discussion of checking assumptions in the past week on the same chapter, if you remember, but we did not go over the confidence interval. So to calculate the confidence interval intercept, that's the intercept, right? Right click, columns, lower 95, appears right there. Right click, columns, upper 95. Lower 95, upper 95. So 450 negative is between negative 560 and negative 341. That's correct. 4070, 4070, right? 4070 is between 3911 and 4229. That's your confidence interval, upper bounds and lower bounds for intercept and the slope. So it's very easy. You go to the parameter estimate of your fit line, right click, columns, and check the lower and upper 95%. Okay, really quick, show you how to do this using Microsoft Excel as well, just to make sure you know how the calculation works. So you have, let me just delete these. Okay, and put the numbers here. So what's the sample size here? Sample size is 980. I write it here. 980 is my n. And I also need t-value, right? T-stat or t-stat equals to. I just showed you how to do it, right? T dot inverse, T dot inverse, double click on this, probability, this is 95%, so 975. Degree of freedom, n minus 2, 980, so that's 978. That's your t-value. Plus minus the standard error, which is here, approximate, it's going to be approximate to 2, 1.90 something or 2.0 something. Okay, so that number plus minus the standard error multiplied by the standard error plus minus the estimates. That will give you this upper and lower bound. So press enter, 1.96239. So I multiply this by standard error of, let's do intercept first, intercept. Give more space here. Equals to, so this is for standard error of intercept. Where is it? Standard error of intercept, 55. Just want to type it, 55. 0.9068. And what's the standard error of slope? Just type it in. So I really want you to do this yourself and make sure you understand how this calculation is done. 81.10826. Now I have the standard errors of both intercept and slope. I have the t ratio of 1.96239. All I have to do is to plus minus the intercept itself. So what's the intercept? Intercept equals to, the intercept is say equal to 450.7376, and the slope is equal to, let me put this all right inside. Okay. The slope is 4070 point 5355. Now I can calculate the confidence interval, right? CI equals to, so CI, or maybe I'll write lower C, lower 95% maybe. This is for the intercept. For the intercept equals to, so all I have to do is to type the intercept, one time minus, one time plus, minus the t-stat multiplied by standard error of intercept. Negative 560. Looking back here, Is that correct? Negative 560. Negative 560. Do you see that? What's the upper 95% of intercept equals to? So equals to, again, same formula, just this is with a plus, right? So it's intercept itself, this time plus, and t-stat multiplied by the intercept multiplied by the SE. Where's the SE? Oh, I made a mistake here. So I have to put the intercept itself and then plus the SE of the intercept multiplied by the T. T is 1.96. Negative 341, negative 341. It's the same number, right? And then same goes with the slope. You can do it yourself and calculate it and see how it works, okay? So these are the confidence intervals for, in fact, intercept and weight. And which one is it on the slides? These are actually slide number just need to make sure you know where it is. This one, this one. That's slide number 24. So slide number 24, we just worked on it, okay? It's right there, upper bound, lower bound. You just right click on primary estimates, column, and 95, lower 95, upper 95. And then let's do the other one, the prediction formula, which is down here on this slide right there. Number 38, slide number 38. Let me show you how to get that one. So you are looking around the red triangle here. That's where you always get your additional information, red triangle. And do you see the individual confidence limit formula? Individual confidence limit formula. And also the mean confidence limit, but this is the one that you can use for most problems. For some problems, the mean confidence limit formula will answer, but individual will answer most of your questions. So click on that. When you click on that, what happens is, looking back to your data set, that's my data set. Look, at the end of the data, there are two columns added. Upper, lower 95, individual. What does it mean, individual? It's because, do you see that say x new? For a specific new value of x, it will give you a specific confidence interval around the new y. So you will give a value for x, it will give you a confidence interval around y for you. Look how it works. So you have to, these are for already available values. So already price, already weight given, these are the confidence levels. But if I go to the end where I can find an empty point here, let me see. Okay, down here, do you see down here? I click for weight. For a weight is x, right? Weight is the explanatory variable. So let's say give like 1. I want to know for 1, what's the confidence interval? I press 1, I press enter, looking to the right-hand side, it's empty right now, but it's going to calculate the confidence interval for you. Look, that's the calculation for confidence interval. So you give it x new, it will give you the confidence for y new. All right, so give another value, give it 2. If there is a 1 unit increase, what's the change in the confidence? If you give it a 3, what's the new confidence? So some of our questions will ask you that confidence interval for the prediction. That's how you can get it. So where to check other assumptions? Other assumptions like normality of residuals, same. So go to the red triangle for residuals and save residuals. residuals will be added to the last column of your data, residuals, right? So what's next? You want to do analysis on residuals. X, or explanatory variable, goes to X. Instead of price, I want to use the residual of price. And click OK. And what I need a fit line. Okay, look, there is a triangle here that shows we don't have similar variances. Variances are changing. The variation is changing, is increasing. There is a pattern. By moving to the right, there is a pattern, right? It's increasing. How about normality of residuals? I can actually click here on the red triangle and say plot residuals, right there. Plot residuals will give me all other analysis I need for residuals. Okay, so normality of residuals should be down here. Yes, it's right there. So you can see that majority of these data are outside that range. That's the upper and lower bound. And majority of this data are actually out of the boundary of upper and lower around the quantile plot. So that's your quantile plot right there. And majority of data are outside the range. Do you see that? That means the data is not, the residuals are not normal. The residuals are not having similar variances. It has to be like a rectangle or a circle, symmetrical. And also we can see there's a pattern here. There's a pattern. By moving, by increasing weight, there is a change. There is an increase or decrease in there's a pattern here, right? So none of those assumptions have met. As a result, this model that we created is not really a reliable model. We need to actually work on this model to make sure it becomes, normally by removing some outliers, you can actually make the model more reliable.